This video is the first video on u-substitution. All right, so I want to look at a function f of x. Let's say we've got 3x squared minus 7 to the, say, 12th power. And I want to review how to find the derivative of that. So if I wanted to find the derivative from Calc 1, we remember that you apply the power rule. So you do 12 times 3x squared minus 7 to the 11th, but then times the derivative of the inside, which is 6x. And so then if you multiply that together, you get 72x times 3x squared minus 7 to the 11th power. Okay, so what we've been working on is finding antiderivatives. And what we want to start doing is looking at problems like this. So if I had the antiderivative of 72x times 3x squared minus 7 to the 11th dx, we're trying to find a function whose derivative ends up being 72x times 3x squared minus 7 to the 11th power. Well, because of what we just showed, the answer is 3x squared minus 7 to the 12th plus c, because we know from above that if you take the derivative of that, you get 72x times 3x squared minus 7 to the 11th power. Most of the time, if you have a problem like this one, we don't have the problem above it where we found it by taking the derivative. And so what we'd like to do is come up with a process that takes you from this to this answer. And so in order to do that, we use a process called u-substitution. And so we're going to go through that, and the goal of this video is to get the process of that down. We'll do a future video on why this works, and then we'll do more videos on harder problems related to u-substitution. But right now, we're trying to get the basics of it down. So I want to look at a problem from the beginning, and we're just going to go through what happens in order to do this problem. So let's say I have the integral of 7x squared times 5x cubed minus, let's say 3 to the 9th power dx. Okay, so when we do this problem, what we end up doing is what's called u-substitution. When you're doing u-substitution, we're still going to match one of the 11 basic forms, but instead of the forms being like x to the n dx, we're going to want either u to the n du, we're going to want 1 over u du, or we're going to want e to the u du, and then we've got the 6 trig forms with u and du instead, and then we've got the 2 inverse trig forms with u and du instead. And so if you notice in each of those, it's u to the power du and 1 over u du, not dx. And so when we do problems like this, we kind of follow 3 broad steps. So the first step is we pick u. And the kind of thought process is that our goal on problem 1 is we're going to try to make it match one of the forms. And the form we're going to try to make it match is u to the 9th du instead of x to the 9th dx or x to some power dx. We're going to try to make this match u to the 9th du, and we'll talk kind of more about how to pick that later. It's not an exact thing as far as how to know what to do, but here it's kind of the main thing is we've got a bunch of stuff to the 9th power. So given that we're going to try to make it match that, we'll do the actual problem in red. We would choose for u to equal 5x cubed minus 3, because then this problem on the left has u to the 9th in it. Once you pick u, you find du. And you find du based on what you chose for u, not necessarily based on what's in the problem. So we define du to equal the derivative of u times dx. Okay, so we're going to define du to mean the derivative of u times dx. So we come back over here, and when we pick u is 5x cubed minus 3, then du is the derivative of that, 15x squared, times dx. Okay, so we pick u and we find du. And then the third step, which takes some work, and in some cases takes a lot of work, is we force the problem, or so we make the problem, manipulate the problem, to match the form we want. So in this case, we want our goal u to the 9th du. So we're going to mess with stuff in the problem to make that happen. So the first thing I'm going to do is I'm going to say, okay, this integral is equal, and I'm going to put the 5x cubed minus 3 to the 9th at the beginning. And I want that there because then I've got the u to the 9th. Remember that u is 5x cubed minus 3, so I've got u to the 9th at the beginning. I'm going to pull the 7 out of the integral because we're allowed to pull constants out, and it's not part of the u or the du. And so when we have that extra constant there, most of the time we're going to end up pulling it out. It's important that you can pull the 7 out because it's a constant, but you cannot pull the x squared out. So we're going to move the x squared next to the dx. And we're just going to rewrite it in this form. And so on every problem that you're doing, every step you do within an integral, you should be questioning two things. One is, why are we allowed to do what we just did? And two is, why do we want to do what we just did? So the first question, why are we allowed to do this? Well, I'm allowed to pull a constant out. I'm also allowed to reverse multiplication, and that doesn't change the answer. So we pull the constant multiple out and we reverse multiplication. That means these two things are still equal to each other. That's why I'm allowed to do what I did. Why do I want to do what I did? Well, I'm trying to get it to the goal of u to the 9th du. And so I've got the u to the 9th at the beginning. Now, if we look closely at what du is 15x squared dx. And over here, I've got x squared dx. Remember, I want du at the end of the problem. So I'm missing a 15. So what we're going to do on the next step is we're going to put a 15 in. Okay, so I choose to put a 15 there. Now think about what happens. So when I go from that second step, the x squared dx, to 15x squared dx, what really happens there? Do I add 15? Do I multiply by 15? Did I divide by 15? Did I subtract 15? So to go from x squared to 15x squared, I multiplied by 15. I'm actually not allowed to do that. So you can't just randomly multiply problems by 15. That changes the problem. But I am allowed to multiply by 1. So if I choose to multiply by 15 there and by 1 over 15 outside, now 1/15 and 15, when I multiply those together, I have really multiplied by 1. I'm allowed to do what I did because I didn't change the value of the problem. I just pulled the 1/15 out. The reason I want to do what I did is now I've got the du at the end of the problem that I want. So the 15x squared dx matches the du that I've got over here on the left. So if you look closely, I've got u to the 9th du, and I can rewrite the problem that way. So I can go ahead and multiply 7 times 1/15. This is u to the 9th, and this last part's du. And let's just kind of go through and circle that. So the u here is the same as the u here. The du that I've got triple underlined is the same as du here. And so I'm replacing those there. So I've got the u here, and then I've got the du here. And now the whole point of that is let's ignore everything above that and look at just that problem. If you were given that problem and had no idea we were doing u-substitution or anything like that, We're just trying to do the antiderivative of u to the ninth du. Well, the antiderivative of u to the ninth du is 1/10 u to the 10th plus c. And so the idea was doing all of this got it into the form that we wanted. We've got something that matches the power rule exactly, so then we can apply the power rule. It has to be so that the variables match. So it's u to the ninth and then it's du. If it was u to the ninth dx, it wouldn't work this way. So because we were able to get the du, we're able to treat it as though it's a brand new antiderivative. Once we're done now, or once we've done that, we've now gotten rid of the antiderivative. We have an answer in terms of u. The problem with that is we made up u. And so we replace u again, so we get 7 over 150, but instead of u to the 10th, we're going to write it as 5x cubed minus 3 to the 10th plus c, and this is the answer. Okay, so like I said, right now in this video, the goal is to get this process down. There's definitely some things here that are questionable as far as the theory behind what we're doing, but I want to go through some examples today and really get down what happens. Later, we'll talk about why this works the way it does, and later we'll talk about how to know when to do this, or what happens if you notice the du had 15x squared, it had x squared, and x squared was in the original problem. So we'll talk more about what if that x squared isn't there, and some variations. But right now we want to just focus on the process. So we first pick u, we figure out then based on that what du is, and then we manipulate the problem to match the form that we want, one of the 11 forms that we're kind of using all the time. So there's 3 basic ones I've got on the top right, the 6 trig, and the 2 inverse trig. Once we get it to match that form, you then apply the rule. The du goes away like dx goes away when you apply an antiderivative rule. It's weird that that happens because du is 15x squared. There's a good reason for that, and we'll show that in a future video. But for now, when you get it to this form, this u to the ninth du, you apply the antiderivative rule. U is still there, but du is not. Then you replace u with whatever it was. Okay, so I want you to take a minute and try this next problem. It's almost identical to the problem we just did, and we'll go through it quickly here in just a minute, but I want you to try the problem. So please pause the video. We'll say to the 19th power. So please pause the video, take a few minutes to work the problem step by step, and try to show the steps just like we did on the previous problem. Okay, so when we're doing this problem, we're going to think our goal is that we would like the problem to match u to the 19th du. And kind of right now, the reason for that is we've got a bunch of stuff to the 19th. So we're going to choose for u to equal 7 minus 6x to the 5th. Du then is the derivative of that, so it's negative 30 x to the 4th dx. We're going to move the stuff around to make it match u to the 19th du. So I'm going to pull the 3 out because we don't need it. I'm going to put the 7 minus 6x to the 5th to the 19th at the beginning. I'm going to put x to the 4th next to the dx. I'm now closer to the goal u to the 19th du because I have u to the 19th at the beginning of the integral. For the du, I am missing the negative 30 part. So I'm going to multiply inside by negative 30. But in order to do that, I also have to multiply by the reciprocal, which is 1 over negative 30. I want to do that because now this part at the end matches the du over here. So I've got negative 30x to the 4th dx, negative 30x to the fourth dx. That's the same thing as du. The 7 minus 6x to the fifth, that's the same thing as u. So when I do the problem and rewrite this, I can first of all multiply those fractions and cancel the 3 with the 30 and get negative 1 over 10. I can replace 7 minus 6x to the fifth with u, and whoops, 19 the whole way, sorry about that. So go back, and these are 19s. And I can replace negative 30x to the fourth dx with du. Now I've got the problem in a form that we know how to do. It matches the power rule exactly. So we apply the power rule. We get negative 1/10 times 1 over 20 u to the 20 plus c. Multiplying those together, I get negative 1 over 200. But instead of u to the 20th, I have 7 minus 6x to the fifth to the 20th plus c. And that's the answer. Okay, let's do a third example. Let's do the antiderivative of 4x e to the 5x squared dx. So again, we're looking at the process of this. We'll talk about rationale and how to pick out what to do in a later video. But here what we're going to do is we're going to try to match the form e to the u du. Okay, so we're thinking we should try to match the form e to the u du more or less just because it resembles that. If we let u equal 5x squared, then the part that we have as the exponential, the e to the 5x squared, is obviously e to the u. In that case, then du is 10x dx. So our goal is to get e to the u du. We're going to follow the similar process to what we did before. We're going to put the e to the 5x squared at the beginning of the integral. That gets the e to the u at the beginning that we want. The 4 is not part of the u or the du, so we're going to choose to pull that out. We cannot pull the x out, and the x is part of the du, so we put the x at the end next to the dx. We've got e to the u, we almost have du. So we're going to multiply inside by 4, we're going to multiply inside by 10 and outside by 1 over 10. So I want the du to be 10x dx, so I multiply inside by 10, outside by 1 over 10. Now if we notice, this 10x dx is the same as du. This 5x squared is the same as u. So we can rewrite the problem as e to the u du. The part outlined in purple, the 5x squared, is replaced with u. The 10x dx outlined in blue is replaced with du. 4 times 1 over 10 is 4/10 or 2/5, so we simplify it down to there. Now we look at this last line as though it's a brand new problem, ignoring everything above it. The antiderivative of e to the u is e to the u, because it's e to the u du, so we get 2/5 e to the u plus c. That's not a good answer because we made up the variable u, so we're going to replace u with 5x squared and get 2/5 e to the 5x squared plus c. Okay, let's look at another problem. Okay, so if I have 7x squared cosine of 5x cubed, I think it's fairly clear that the goal would be that we would want to match cosine u du. And like I said, we'll talk more about how to pick some of that out later. There's not always a definite way to do it, but here the main thing is we've got cosine of 5x cubed. So we'll go through this one quickly. We're going to let u equal 5x cubed. Du then is 15x squared dx. We're going to pull the 7 out. We're going to put the cosine of 5x cubed at the beginning, and we're going to put the x squared next to the dx. We need a 15 with the x squared, so we're going to multiply inside by 15 and outside by 1 over 15. That gets us 7/15 cosine of u du inside the integral. The integral of cosine u is positive sine, so we get 7/15 sine u plus c, which is 7/15 sine of 5x cubed plus c. And that's the answer. Okay, let's do a similar example. Let's say this time I have e to the 4x sine of 3e to the 4x dx. So when we're doing this, there's a couple different options, I guess, but the main thing is we've got sine u du, or we've got sine of something. So we're going to try to match sine of u du. It might also be that we would think to match e to the u du. The problem with that is if we're going to match e to the u du, u would be 4x, and then du would be 4, and there's too much extra stuff going on in order to make that work. Here, when we try to match sine u du, u is 3e to the 4x. Du then is 3e to the 4x, but times 4 because of the chain rule. And so du is really 12e to the 4x dx. That means when we go back and do the problem, we're going to move the sine 3e to the 4x to the beginning. We move the e to the 4x to the end next to the dx. There's no constant to pull out, but that's okay. We need a 12 inside, so then we need a 1/12 outside. That gets us 1/12 integral sine of u du. The integral of sine is negative cosine because the derivative of cosine is negative sine. So we get negative 1/12 cosine of u plus c. That gets us an answer of negative 1/12 cosine 3e to the 4x plus c. And that's the answer to this problem. If we have x, secant x squared, tangent x squared. A little bit weirder, but I want to go through one that matches a form where u shows up twice. So the form we're going to try to match is secant u, tangent u, du. That means that u is going to equal x squared. And so then du is 2x dx. So we put secant x squared tangent x squared at the beginning of the problem. And we move the x next to the dx. If it was like 4x or 5x, we would pull the constant 4 or 5 out. we now need a 2 with the x dx. So we multiply inside by 2 and outside by 1/2. That gets us 1/2 integral secant u tangent u du, because the 2x dx is the du. The antiderivative of secant u tangent u du is secant u plus c. So we get 1/2 secant u plus c, which is 1/2 secant of x squared plus c. Okay, I want to look at a few more examples. So let's say I have x over, we'll make it 3x over 5x squared plus 1 dx. This problem looks somewhat like an inverse tangent form. It turns out that it's not, and we will talk extensively about that in a future video. But here, the form we're going to try to match is 1 over u du. And so if we do that, u is 5x squared plus 1. Du then is 10x dx. And because of the way, whoops, make that a little more legible. Because of the way the algebra works with fractions, we can think of 3x over 5x squared plus 1 as the same thing as 3x over 1 times 1 over 5x squared plus 1. So we can pull the 3 and the x off of the top of that fraction. And so because we're going to try to get this du at the end of the problem, I'm going to pull the 3 out. I'm going to leave 1 on top of the fraction, and I'm going to put the x next to the dx. And it's technically like x over 1 and 3 over 1, but those are the same things as 3 and x. And so now all I need is a 10 for the du. So I multiply inside by 10 and outside by 1 over 10. So then I get 3/10 integral 1 over u du, which is 3/10 natural log absolute value of u plus c. U is 5x squared plus 1. Oops. And so we get natural log of 5x squared plus 1 plus c. You may notice that I dropped the absolute value. The reason I can do that in this problem is because u is 5x squared plus 1. X squared is always 0 or bigger. So then when I do 5x squared plus 1, that's always positive, which means the absolute value of 5x squared plus 1 is just itself. It would be okay if you left the absolute value on that, but it's not as simplified. I'm not real picky about something like that. In some cases, you could not drop the absolute value. If you had 5x cubed plus 1, you could not drop the absolute value because the x cubed could be negative. Okay, so there are several problems where if we were to do something like this, we would want to rewrite the problem first. So here, that matched 1 over u du. Let's say we had a similar problem where we had 3x over 5x squared plus 1 to the 4th instead. Then it would end up being that it's 1 over u to the 4th. But rather than that, what we would want to do is have a negative 4th power. So the way you would want to work that problem out is to rewrite it with a negative 4 power. And now it's like the first few problems we did on this video. If you have a square root, the same type of thing happens. And we'll actually work one example with a square root in a second. But if I had, say, 5x to the 3rd times the square root of 8x to the 4th plus 1 dx, we would rewrite that with a 1/2 power. And now it's similar to the problems we did at the beginning. I want to work one problem like that, but on the first homework set on u substitution. There's lots of different situations like that where you have to do small manipulations, and you'll have solutions to that to help you through it. Let's look at the integral of the square root of 6x plus 5 dx. So on this problem, we're going to rewrite it as 6x plus 5 to the 1/2, kind of for the same reasoning we were talking about a few minutes ago. And now we're going to try to match u to the 1/2 du. So the goal on this one is to make it u to the 1/2 du. So we're going to let u equal 6x plus 5. And now du is just 6. And this could happen on any of the forms where du is just a constant. And that's okay, especially if there are no other x's to deal with. So there's nothing to move around here, but we do need a 6 with the dx. So to change dx to 6 dx, technically we're multiplying by 6, which means we're going to multiply outside by 1 over 6. That gets us 1/6 integral u to the 1/2 du, which is 1/6 times 1 over 3/2 u to the 3/2 plus c. That gets us 1/6 times 2/3 times 6x plus 5 to the 3/2 plus c. That gets us 2 over 18, or 1 over 9, times 6x plus 5 to the 3/2 plus c, and that would be the answer. Okay, so at this point, we need to get very comfortable with this process. So you should do the problem set called u-substitution 1. There's a lot of problems on that problem set. There's also solutions to that problem set. So please work those. There are a few mixed in that are probably not u-substitution, and I'm trying to get you to see how to know whether it's u-sub or not based on the differences between those problems and the problems around it. So try that and get comfortable with this process before the next video. In the next video, we'll go through the rationale as to why u-substitution works the way it does. Thanks for watching this.